All right. Hey, everybody. I'd like to welcome you to the Audio Programmer Meetup. This is the February edition, getting into Valentine's Day. And can you believe that we're already about over 10% through with 2025 already? The year is flying by quick. And today I have the pleasure of being joined by the physical audio team. So we have Craig Webb, Michele Ducceschi. We have Stefan Bilbao and Gadi Sassoon. And they're joining us today, and we're going to be talking about physical modeling and synthesis. So a lot of really amazing stuff that's happening in this world, and they are on the forefront of what's happening in the world of physical modeling. Things like how do you model an instrument that's from the 1700s or 1800s? You can't take it apart. So how would you physically model? So this is a problem space that we're going to be talking about today. Before we get started, I'm going to give a shout out to our sponsors, Focusrite and JetBrains. Thank you for sponsoring the Audio Programmer Meetup. Without you, it would not be possible. So thank you to Focusrite and JetBrains. And also want to talk about our community. So we have over 11,000 members in our audio programmer community now, developers of all different experience levels. And we welcome you to join us for free. You can join on our website, theaudioprogrammer.com/community. We also offer development and recruitment services as well, and you can find out about those on our website. And without further delay, I will go ahead and pass it over to the physical audio team to go ahead and introduce yourselves, maybe talk one or two sentences about what you do with physical audio before we jump into the talk. So let's start with Craig.
Hi there. Yeah, so I'm Craig Webb. I run physical audio. I've been doing it now for like 4 years, I think we've been going. And so I'm basically the CEO, and I actually make the plugins. That's my role. I also work at the University of Bologna on the NEMUS research project.
Yeah, that's a project that I'm running in Bologna in Italy currently, and it's devoted to restoring the sounds of historical musical instruments that are currently sitting in museums completely damaged. So the idea is to take all the experience we've been collecting through the years with these sort of virtual and crazy physical models we came up with, but with a very specific purpose of making them sort of more realistic and targeted towards reproducing the sounds of harpsichords and early keyboard instruments like that. So we will be talking about it shortly, I guess. And I guess Stefan is sort of involved in that too, not in NEMUS, but in the more general picture of physical
Yeah,
modeling, obviously.
yeah. So I'm Stefan Bilbao. I'm up here in Edinburgh, and I've known these guys for forever. So both Craig and Michele were students on the master's program here, like 15 years ago. Is that right? And then
Yeah.
like it's gone off in all these crazy different ways. It's been really fun. We had a big physical modeling based project for a while in the kind of 2000 teens that they were both involved with, and now we've got this company going, and Michele has the Nemos project, and it's going well actually. So
Yeah, hi, my name is Gadi Sassoon. I'm a composer, performing artist, and music producer from Milan. And I'm somewhat of an unofficial member of the physical audio team, or slash mascot, really, because I've been involved with them for a decade, really, with the research originally on a level of outreach, in that I was a resident composer for the NES project, which was a project that Stefan was running at University of Edinburgh. And I've made music with the algorithms created by the NES team and physical audio, and now the NEMUS team for at this point a solid decade. And now we've started sort of really also developing some things together.
Fantastic. So before we go into the talk, I'll go ahead and just talk about the presentation. The name of the presentation is called Physical Modeling, Historical Keyboards and Granular Synths, Exploring the NEMUS Project. And the talk abstract is, in this talk, Michele Ducceschi and Craig Webb from the University of Bologna and Stefan Bilbao from the University of Edinburgh will be joined by Milan-based composer Gadi Sassoon. Together, they will discuss the latest advancements in physical modeling research and the NEMUS project, which focuses on designing historically informed MIDI controllers for museum collections. Additionally, they will explore physical audio and Gadi Sassoon's newest collaborative plugin, Granular Synthesizer with a physical modeling twist. Without further delay, I'll turn it over to physical audio. Take it away.
Cool. Yeah, so I think I'll start really with just basically some updates on sort of what we've been doing for the last couple of years. Yeah, we last did this talk, what did we say, 3 years ago? So yeah, we have a few updates. So let me share my screen. So yeah, so last year we released an update to our prepared string instrument. So this is called Prep 2, and this is based on two strings which have a rattle and then this dynamic fret thing, and the strings collide with these objects as you play the thing. So it's quite a simple model, but we've kind of added like LFOs and some modulation stuff, and there's like a full effects rack down here. And so yeah, let's just have a quick listen to see what this sounds like. Cool. So another instrument we released, this was the year before Prep 2, and this is called Modus. So Modus was actually our first go at doing an instrument based just on modal synthesis. So our other instruments are based on what's called finite difference modeling, but with this one, it's a pure modal approach to doing the actual calculations like in the engine. So there are kind of like pros and cons to the two different approaches. But the main thing with this is that we can actually do both one-dimensional and two-dimensional objects. Yeah, so we have strings, in this case, attached to a plate with these connection guys. So there's actually a couple of like different configurations of this thing. The first of which is connected strings again. So we can have so we can have 3 strings or 4 strings. Like. And you can hear all the kind of non-linear effects that are going on due to the way that these things are connected and the connection element. So another configuration is called where we have strings which are connected to the plate. So here we've got 2 strings, which are these guys. And then each string has 2 connections down to the plate. And here the plate is basically acting like a soundboard. And then a final configuration here is where we actually have 2 plates. Yeah, so we ditch the strings a little bit, and we've got 2 plates which are connected together. And you can see we've got these connections which have a little gap, and these are like rattling connections. There's actually like a few different ways we can excite the plate. So we have like some oscillators, like a sine wave or a sawtooth or a sine wave. Or we can actually like hit the thing like with a mallet. Yeah, so we're applying an excitation like to the top of the top plate. Sounds like this. So what's happening there is as we turn up the strength of the connections, you're getting all this like non-linear effects going on as you strike the top plate. Now, another thing that I'm working on is how to sidechain audio actually into the instrument. So in this case, we're taking a sidechain from an audio track, feeding it into the instrument, and then using that as an excitation signal for the top plate. So here's like cool. Okay, so this kind of leads to the sort of general idea of doing like augmented instruments. Yeah, so having like hybrid systems where we've got like a real acoustic object and maybe a virtual acoustic object, and like combining like the two things together. So yeah, that's kind of led or leads into a lot of other stuff that we've been doing, certainly over the last sort of year, year and a half. Gadi, do you want to sort of jump in on that stuff?
Yeah, sure. The concept of augmentation is something that I have been pleasantly surprised that we aligned on, and because I've been sort of separately working on performing on violin, electric violin, and trying to get a better sound out of the electric violin. Partly also to overcome a physical injury that I sustained during COVID. And so basically doing pitch tracking and then trying to layer different kinds of elements on top of the electric violin signal that if anybody is familiar with is not the most stellar of raw materials generally. And
violin, like as a side chain into modus, into the plate.
as well, yeah. So basically, the final stack on the performances that I was doing about a year ago was, one or two, in fact, instances of modus with side chaining, another instance of modus with instead MIDI from a Max for Live pitch tracker, and then just sort of like other bits of subtractive synthesis and stuff like that, just to create a corpus that basically like a full body of sound out of just one singular musical gesture, right? So like the idea in a lot of ways was to be able to show up on a big sound system and be able to just play one violin and get a whole orchestra, quote unquote, to come out of it. But yeah, a year ago, off the back of that, I was invited to a festival at MPAC in upstate New York. MPAC is this really stellar venue in Troy, New York. And it was a billed as a transducer festival, right? And so it was an opportunity for Michele and I to riff on an idea that we'd been toying around with for a bit, which basically was, okay, over the course of nearly a decade, I'd been working with algorithms that took real world objects and translated them into the digital world, right? This is a very crude sort of music maker's perspective on what is happening. But so the idea for me was, okay, can we go the other way around and do something, create a tangible object from algorithmic calculations, really, right? Previously, I'd done a piece at a studio in Stockholm where I was using the algorithms from the Railer at the time, or maybe early incarnations of Modus, and feeding them through a physical plate, and then feeding them back into the side chain and getting these interesting sort of non-linear types of feedbacks through that. So that's what we set off to do, right? To create plates, essentially, to create interesting plates that I could excite with a transducer, of which actually I've got one here. And these are really just really crude plate reverbs, essentially, that have been slashed to create a variation in the acoustic properties of the plate itself. The modes of resonance of the plate. Hopefully, it won't topple over. Otherwise, it would be
You tap
painful.
it, like is it going to make a? You tap the plate now.
If I tap the plate now, it's going to go. It sounds kind of like a crappy cymbal. ish. Yeah. Doesn't do much unless you actually send a vibration through it. You know what I mean?
And that's what you've got stuck on the front there.
Yeah. So this is a simple, cheap transducer. Really, this is actually a contact speaker. So these are designed to play music on things like shop windows or inside plaster walls, typically. This is the full spectrum one. There's bigger ones for sub frequencies. They are surprisingly effective, although one of the sort of like hindsight things that came off this is that if you have a polarized metal, then this thing has a magnet in it. So you have problems with that. But yeah.
Well, we had a little incident in the lab, Gadi. Speaking of that transducer, right? Like Gadi took the plates over to the lab in Bologna to take some measurements after we started working on this newer plugin, and we just ran some crazy input power into them, and all of a sudden we started smelling burnt, and we didn't know where that came from. And all of a sudden we realized that we drove the transducer, such high, input energy that it basically burned down and melted. So we learned something from it, at least, because we had a shooting scheduled, not the day after, but kind of close to that. So we had to, collect new equipment and make sure that, we wouldn't run the thing at high input power during the shooting, because obviously that would have ruined everything. So that was a lesson to be learned.
I've been very generous here, because what happened is I got excited and I just went off the scale with going straight from max into the amp.
Right.
And
yeah.
There's a real rookie mistake there, and just blew the amp and the transducer, didn't I? Yeah.
Yeah, I mean, it's still lying around in the lab, but I never really tested it, so I don't know whether that was spared or it's completely dead. But we'll figure it out, I guess, in due time.
Yeah, I still haven't figured out why they always smell like burning after a while. Anyway, so something is definitely hot in there. But I mean, part of it is a question of sort of moving forward with this kind of piece, is scaling the right amp and the right size transducer to the right sort of scale and thickness of the plate, right? Because otherwise it's I'm just driving it as hard as I can to get a response from the plate, right?
The idea for the cuts, where did that come from?
That was Michele's idea, actually, because I wanted them to look interesting, but I also wanted them to have some kind of differentiation, because there's 4 of these, right? This is just the one, but they have cuts in 4 different directions: vertical, horizontal, and 45 degrees either way. And so Michele suggested something inspired by Lucio Fontana, as an Italian artist that used to slash, like his entire art was just like taking a blank canvas and slashing it. So a little reference there, but also, yeah, it worked to that extent, and also the placement of the transducers is so that they don't interrupt any primary modes, I believe, or they don't lie on a primary mode. Remind me, Michele. Sorry, I'm rusty on that one.
Yeah, that was kind of the idea, to sort of test out various positions of the transducer to get different effects. Usually for a freestanding plate like that, you would place the transducer near the edges, because you know that you don't have nodal lines around there. Here, I guess you kind of have an internal free edge near the cut somehow, but I don't know how the nodal lines really line up with it. But I guess it doesn't really matter, in the sense that probably you kind of get more or less the same effect by attaching the transducer, around the plate in different areas. But we kind of ran some studies at some point, so we got this simulation software, and then we actually drew the geometry of the 4 plates with the 4 different cuts, and we started computing all these very beautiful vibration patterns. And then you could see basically the frequencies change and the modal shapes change according to how the cut was placed in the plate, and that was just like really beautiful to see. And in terms of acoustics, I mean, obviously you'll get a change according to where the cut is and where you place the transducer, but I'm not sure we can, I'm not sure that basically your performance is based around that all that much. It's more like it's more like a trademark, it's more something that is very recognizable in the plates. It's something that people recognize. And I think it works very well in terms of having something very unique and very visual that people can recognize and go, oh, well, what is that? Why is there a cut? And it kind of really blends in very nicely in that respect. We did model the plates precisely when they came to the lab. So we ran some very basic measurements. We stuck an accelerometer on the plates, and then we hammered them with a little impulse hammer, and then we measured the resonant modes in that case. So we were able to extract a mathematical model from the measured response and implement that into a plugin. That was a very early version of what we're currently working on. So yeah, it's basically a very sort of lo-fi plate reverb in some sense, because we couldn't excite many modes because the hammer I had was tiny. So we couldn't really, excite the plate with a lot of energy in that case. And the plugins were okay. They were kind of lo-fi, but they worked in the sense of actually reproducing this sort of very metallic resonances into it. So you could really zoom into the resonances or and hear all the transients. So that was fun. But then yeah.
Hey, can I just ask? So you guys are driving these into the nonlinear regime, though, right? Like, so when Gadi drives it, you're getting the crashes and stuff that you would out of something at high amplitudes, right? So, but
yeah, absolutely, yeah, you do. But we also had a lot of videos from where we were testing it in the lab, and after measuring all the resonant frequencies, we started exciting the plates at the resonances to see whether we could excite these sort of standing wave patterns, and we could. So we had a lot of beautiful videos from the lab where you could see the plate basically moving in one modal shape, so basically exciting just one resonance. And then of course during the performance, I guess that I'm not sure whether that's actually true all the time, but certainly when we shot the video, there is a part in the beginning where we excite the plate with this very sort of high amplitude sinusoids, and you definitely get all these rambling effects that are typical of nonlinear plates. But I guess that these mostly kind of work in the linear regime during normal sort of performance. So I guess that linear theory kind of works okay for the purpose of having a reverberating unit at the end of the chain in the digital plugin. Yeah. But yeah, certainly you do get a lot of nonlinear effects out of them.
and also, can you easily sort of hear like the differences in where the slash is on the plate, or is that like?
Well, yeah, not so much, just because the cuts kind of really affect the higher frequencies and not the lower frequencies all that much, right? Because they're small. You will see, yeah, if you model them, you will see differences. But then again, the plates are so full of resonances that they kind of mix together, and it's really hard to recognize one plate from another plate just by listening to it. Probably the transducer, the location of the transducer is what affects the sound the most. So that's sort of like your high pass or low pass filter in some sense, whether you place it around the edges or close to the center. It will sort of low pass or high pass the output sound. But they all sound different. They all sound different. They all have their own characteristic sound, and I guess that partly it's because those are very sort of rustic plates and rusty. So
increasingly rusty, yeah.
Yeah, and increasingly so. So you will get all these effects coming out of the fact that these are not supposed to be perfectly polished plates and copies of each other. So you will hear differences. Whether the differences are entirely due to the cuts or not, it's a different thing, and I don't think it is in some sense. But like I said, I think that the cut works very well because it's conceptual, and it's very recognizable, and yeah. So I think yeah.
We've got a little video clip from the actual performance. Maybe now would be a good time to have a quick look.
Yeah, sure.
Yeah.
Yeah. So maybe it's a bit less abstract. Let me see. Okay, share desktop.
Yeah, maybe you do have close shots of the plates vibrating, Gadi, in the beginning.
I do
of
in
the
that
video.
clip, yeah. I also
Yeah.
just fished out this, which is one
Right,
of the initial simulations that were done. This is for one of the 45-degree cuts.
Yeah.
Sort of like seeing what the actual modes of vibration are for different frequencies. And conversely, this is an actual series of resonant frequencies as measured in the lab, which I was then able to use further down the line exactly in the performance I'm about to show you, where I use sine waves. And really, in terms of the different qualities of the plates, it depends on what you drive them with. But I'll get to that in a second. I'll just show you this little clip first. Okay. Yeah, so that's a little snippet from that beginning of that performance.
That's pretty cool.
I can actually maybe play you another bit if you bear with me just 1 second. But yeah, so that's when we got into the sine waves, because I started off playing violin through it, and violin was actually it's a little bit jarring if you don't dial it in just right, because it's just a lot of screeching and metal and stuff, and it gets old pretty quickly. I've played Hammond organ through them. I've played guitar. I've played Buchla. I've played the guitar was amazing. And one of the things that you may have heard there is that there's a lot of panning happening between the plates. So that creates it's things that, depending on how you use it, it's almost like a tangible synth, Okay, let me show you something else really quickly, which would be this. So these are actually melodies created from the resonance tables, which is pretty fun.
Yeah, they definitely move like a lot.
Yeah. And when you hit the right frequencies, they shake. Like you have to be careful not to drop them, kind of thing. So yeah,
that's pretty cool. I actually fetched one of those videos we shot in the lab. Maybe I can show it real quick.
Yeah.
I'll just share my screen. There is no sound, but
when Gadi came to Bologna, within the
so it's this video here, and we were actually looking for these resonances. So we started like very surgically looking for the resonant frequencies of the plates, and basically just inputting a pure sinusoid into the plate, try to match one of the resonant frequencies, and you could get this very nice sort of standing wave patterns in some cases that are really beautiful to watch. So you can see that basically, all the parts in the plate are moving at unison, and it's sort of bending and maybe twisting a little bit too, but in basically just one mode of vibration. So you can really see these things, and that's part of what inspired that early part of the video, Gadi, right? So we thought that it would be good to sort of start filming your performance by just having pure tones going into the plates and just excite them to sort of, you know, activate all these resonances. And again, you know, it's not meant to be a scientific experiment. It's more of a conceptual thing. But the whole idea around, you know, modes of vibration is precisely that, you know. So having these 4 plates and having the resonances and really going back to the building blocks of vibration analysis, which is, you know, resonance, and also somehow, you know, to the very, you know, building blocks of computer music as well, sine waves. So the idea is to basically sort of conceptually connect these 2 things and do, you know, just use the most basic oscillator you could ever think of in a synthesizer, which is a sine wave, and sort of see how that interacts with an analog system like an acoustic plate. And so the connection was precisely done through, you know, the idea of resonance. So see if the sine wave can excite the resonance in the plate and see how we can interact with, you know, this system in a meaningful way that is meaningful for the performer, who is Gadi in this case, but also meaningful for the audience who is listening and watching. So I think that sort of, you know, these ideas sort of, you know, encapsulate what we've been trying to do recently. So I think, I don't know, I find it really beautiful and really fascinating also because it's a step away from what I do mostly, which is, you know, academic research, and always has to be very precise and very sort of mathematical in some sense. So having the possibility to sort of turn all these concepts into a more, you know, artistic endeavor for me is, you know, is great. And having found a partner like Gadi that's been with us pretty much constantly for 10 years now, it's been an incredible resource of inspiration in that sense. Because, you know, I think we kind of touched upon these things last time we talked, Josh, about 3 years ago. But, you know, this whole thing we're doing now basically grew out of what Stefan was doing, you know, years ago in Edinburgh, and Craig and I were a part of his team. So he had this massive project in physical modeling that really led the way for, you know, all future endeavors in the domain. And Gadi came around about 10 years ago when we were all still in Edinburgh, and he started, you know, experimenting with these big systems we had that were all offline at the time and required a supercomputer to run. And it's been nonstop ever since. So a lot of these models now sort of run, you know, on our personal computers. So we made a step forward, partly because we refined the algorithms, partly because computers are more powerful, partly because we made some, you know, necessary compromise in terms of, you know, the freedom we gave users and the parameter space, we give users. So partly is that, but partly is also because, you know, Gadi really helped us a lot in that sense, you know, and, you know, finding, for example, you know, exploring parameter space or using modulation, or understanding how, you know, a performer would approach the idea of working with a physical model, which is likely something they've never really worked before, or even if they did, they're kind of unfamiliar with. So this is, you know, this is just the creative process in the end, and it's good to have both, you know, the actual artistic and creative side, which is Gadi, and then us who are more on the technical side of things. But I think it is really a necessary synergy when you approach this problem, because you know, because physical modeling is very technical. You know, there are a lot of difficult things in there, but at the same time, the product is meant to be used by artists and sound designers. So you also need to understand how, you know, you can make a useful product that people eventually will use. So this synergy is absolutely essential, and I think we are at the moment now where, you know, we're really cruising. We're really doing like something, you know, very beautiful and very useful, hopefully. Which is this new plugin called, can we announce the name of it, Gadi? Tetrad. Yeah, it's a very
Sorry,
nice
I
thing.
muted myself because I was worried the thing was going to topple on me. Yeah, absolutely.
Yeah. So which incorporates this, you know, this idea of plates, but it has a lot of different things into it. So I mean,
the main sort of basic idea for this is like Gadi having done his like performance, or I think you've done like a couple of performances with the plates, haven't you? Like two.
Yeah.
Yeah.
Yeah, I've done a few. Well, here's a picture of the first one that I just found.
Did you do it
Which
in New York, was it?
this was in New York, yeah. This had the plates actually in the four corners of the room in a big sort of ambisonic cube type deal situation, right? So you had actual immersive sound and these four lo-fi plates and that was the first place where I started working playing with it, because here's the idea, right? Like, this is one of the sessions from that video shoot that you just saw. And basically, I'm controlling one of the most important things that I do live with this thing is controlling the surround panner as if it's a quad array, essentially, right? So I'm able to distribute the signal of a single oscillator across these four plates. Well, coincidentally, I've just fallen on this sort of faster rate here, where in the real world, it sounds like kind of AM, but it is really technically, right? Because you're constantly hopping from one plate to the next. And the interesting thing for me then became how, because the video shoot turned out being the beginning of the production of an album, right? And the question that arose from that is, okay, I've got four things in the real world and they sound really quite interesting if you're in the room with them, but suddenly you've got a stereo stage that you have to somehow present this thing into, right? And how do you do that? Because at this stage, we'd already started playing around with the idea of granulation, I'll show you in a second, and with the idea of, and we already had these things, which is the models of the plates. The sort of like, this is the very first incarnation.
This thing here is basically just a modal plate. So each one of these has got a bank of modal oscillators, and it's essentially a plate reverb replicating the modes of vibration of each of the individual plates.
Yeah, as I measured them in the lab. So this comes from the early measurements we did very early on.
Yeah, and obviously this all worked really well, as I said, in an installation / concert type of situation, even amplified, whatever, right? Because you've got four things that are moving in space. But suddenly, if you have to represent this in stereo, I just went down to basics and I said, well, okay, I've got the automation. I've got the automation recorded. I've got the visual of the plates moving. I'm just going to apply amplitude modulation to the signal. So, instead of having it, because instead of trying to somehow present some kind of stereo MacGuffin, I just went. Just recreating the amplitude as it. Sorry, I mean recreating the panning just with the amplitude of the wave, right? Because it's perfectly synced to picture. So in a way, it was a workaround to, post-produce the video, because obviously here I've got the live sound from the room as well. And it's a decent stereo recording of the situation, but obviously it wasn't that there was a lot going on as well at the same time. So it was a question of putting all these building blocks together. And then from that, I made a max patch to somehow try and figure out what exactly this whole process was meant to be, right? So this is the max patch is here in the middle. These are all the prototypes from the plates and this early stage granulation stage that we put between the oscillators and the plates, because we figured it would be an interesting thing to do in terms of, so in some sense, representing the non-linearity, the noisiness of the actual plates in the real world, right? And the kind of like slightly less predictable, in some sense, way. Predictable is not the right word, but the more textural aspects of this piece, right? And so this is just essentially, you've got four oscillators with relative frequencies. It's using the quite excellent MC objects from MSP that they have now. The multi-channel stuff is just is amazing. Would have been a nightmare to produce this any other way. And really, it's of course, it's got the granulations and what have you, but the heart of this thing is this sort of phase shifting amplitude modulation across the four oscillators. So if I just play this is all on the same frequency. I can scale the relative frequencies of the oscillators. Sorry, that's a bit loud. It's very clicky in typical, Max style. It is quite beat me up, Scotty, isn't it? I'm gonna jack up this really crude
clear, what we're trying to do here is create sort of 4 buses of signals that are where each bus feeds one individual plate. That's kind of the
that's kind of the idea, right? It's like, okay, so how do you and they're panned at the moment in such a way that you can hear them in different positions. My Berkeley professors would be proud. So obviously it's the maths is really crude because it's me doing it at this stage in terms of these frequency exponents and things going negative for no reason. But this was kind of like a stage in which I was able to sketch out something for the physical audio scientists to convey the idea in a better way than through language, I suppose.
Yeah, I think this was, very helpful in terms of basically coming up with, a more defined plugin that includes more or less all these features, and that includes also basically the, the framework around it. So, like Craig said, eventually we settled for basically having a system with 4 buses. And each one of these 4 buses is then processed through basically, a filter stage, well, a basic, not a basic, but like an amplitude modulation stage and a frequency modulation, and then through filtering, and then through a granulator, and then again through, the plates. So basically that's what we've been working on for the past few months, and it's a plugin that we're hoping to release soon called Tetrad.
We have a sneak peek.
Yeah.
Let's just have a look at that.
Yeah.
Obviously, we all started with this max patch and these sort of extensions with a little granular unit and stuff. But obviously, the end goal is to put, combine all this into a individual plugin. Yeah. We'll try and share this. Okay, so basically, Gadi designed or sketched out kind of a sort of basic UI for this, of how all these kind of individual units are going to form sort of a bus system and create like a signal flow. So over here we have what will be the sort of originating oscillators. Then we go down to like a mixer matrix, which again is very similar to the max patch. And then we go shift to the right, we have the amplitude modulation stuff. Then we've got 4 buses or 4 units of the granular synthesis part. And then finally, they end up going into some preamps and actually into the models of the plates. Yeah. So this is, we're kind of trying to create this kind of 4-bus system. So this is kind of pretty early prototype. I literally got it to work like yesterday. But I think we can hear some sound at some point. Basically, oscillator. That's kind of like the first kind of stage bit, like trying to replicate what that max patch was actually doing. Yeah. Then the next stage over here, we've got 4 granulators. So this is like doing granular synthesis, 1 on each bus. And there's a couple of views, like there's a quad. Yeah, so that's just just a little sneak peek. It's yeah, kind of a work in progress, definitely. But yeah, we're sort of getting there in terms of trying to get all these elements that originally was like this prototype thing derived from a max patch actually working like in a plugin.
Yeah, I think that really shows. I mean, how do you end up doing a plugin? You know, where does your inspiration come from? You know, and in this case, it was really a long process. Well, we never really meant to create a plugin out of this. It only, you know, the idea came into existence only later on.
Whose idea was this? Like, really?
Yeah, but that's part of the creative
Nobody
process, and I
knows
guess.
really. This is the thing. This thing just kind of came out of his own volition.
Yeah, also because I mean, of course, physical audio is a commercial endeavor, but we never really were just that, right? Because we've always been working basically in academia. So at the same time, you know, we're you know writing all these papers and solving all these problems, and physical audio has always been somehow on the side of all these things. And so we're not purely driven by you know having to sell a lot of plugins in some sense. And this basically gives us the freedom to perhaps explore things that are a little different and maybe not necessarily commercially viable, if you let me. But I think that a lot of people probably following your show, Josh, are interested in maybe knowing like, oh, how do you come up with new ideas for plugins? And for us, this is really that, you know, in this case. So you see where this idea came from. It was just basically a lot of exchanges between us and Gadi, and then Gadi doing this performance. And then for us, maybe jumping in and say, oh, okay, like really we can reverse this process of you know, starting from the real world and coming back to the physical model and embedding all these other things that you've been working on and just, you know, this idea of basic building blocks, resonances and sound waves and sine waves. So that's, you know, how Tetrad came into existence, and I think, I don't know, it's a very fruitful process for me, and I don't know, it's you know, that's basically just the way we work. So
Yeah, can you talk a little bit? There was a question from Wave Sequencer about this, talking about asking specifically about what the workflow is to go from max patch into a plugin.
Yeah. So it's kind of okay. So I basically had to create all these sort of different elements. Like I started prototyping them as like individual little sort of test plugins. So what we were looking at when Gadi had that showing the screen was me like testing out an individual granular synth unit. Yeah. So I didn't have one pre-built. So I had to, I mean, Michele prototyped a little stuff, some little bits in MATLAB. And then from the MATLAB, we always start with MATLAB in terms of prototyping. From there, it's like trying to put together little individual test units to get all the different kind of elements together. Yeah. So yeah, there was like an individual granulator synthesis bit. We had an individual plate plugin, so there were 4 of those to have the individual models of the plates. And then eventually you get to a big sort of jigsaw puzzle of trying to get all of this stuff into a single C++ code base, and then actually to stitch the whole thing together. So I usually go through various like prototype stages. So I think Gadi's had quite a few like early prototypes where you're not bothered about what the thing looks like. You're just chucking controls on the screen and trying to get the engine.
So you said you prototype in MATLAB. Just to clarify, is that you said MATLAB, not
so
Mat?
yeah, we normally do all of our basic initial prototyping in MATLAB. I mean, for Stefan and that, I guess.
Yeah, just a word about that one. I think it's just because of the sort of academic origins of this stuff. Like Michele and I are engineers, right? So that's what we're comfortable with. So there's not really a stage normally where it passes through a max patch. I guess in this case it did though, right? Like there was a max patch for Tetrad or something. No,
Yeah,
or
well, there was this max patch, and then I came up with the idea of a granulator. So I kind of coded it again in MATLAB, which is probably not the best idea because granulation is probably one of those effects where you really need to look after like audio buffers and be very careful the way you design things. So MATLAB is definitely not the best environment for that because you will be working offline with a big chunk of audio and then you will process it in one go. But that's not actually what you are doing in the C++. And because granulation is very much tied to the grain sizes and things, then I guess that the most complicated part of that algorithm is not dealing with the algorithm as such, but dealing with audio buffers. So, but then again, it kind of worked in the sense of understanding, what sort of soundscape you could get out of this, and what sort of sonic capabilities you could get out of this. So it was still kind of useful. It was still a good, back and forth between me and Craig to sort of try to figure this out. But then, lots of things changed down the line because Craig added in a lot of different features like negative grain sizes or negative hop sizes, and repackaged everything in terms of grain frequencies and things which weren't present in my original design.
I mean, we use MATLAB just because it's quick and easy, basically.
Mhm.
Yeah, but that's again, like Stefan said, it's really coming from when we did that as academics. So we would just use MATLAB to do a bunch of things, not just audio. So we were just comfortable using that.
Yeah, and also just for prototyping physical modeling as opposed to like a granulator, like I guess like algorithmically it's complicated and kind of like there's more ways to go wrong actually, I suppose, with it. And there's more debugging that happens, I guess, and it's MATLAB is really easy for that kind of thing, rather than like trying to
Like
do
you wouldn't
everything.
consider like moving to a different platform for prototyping, much.
I don't like. I mean, it works for me. I can't think. You mean like Python or something, or what? Or
Yeah, I mean that would be obviously if you're doing physics stuff, Python would be recovered.
yeah, I mean that's what people are doing these days. So there may be a move at some point. But I don't know. I mean, I guess for me, like when I'm doing physical modeling, I just want to get the sound out, and I don't want to have to go learn another language to do it. So,
And plus,
so I
like
guess I'm
MATLAB's
kind
good
of
for
stuck with
doing
it at this point. You
all
know?
that kind of sparse matrix stuff, working with linear algebra. That's kind of an advantage of MATLAB.
Yeah, that's an advantage, but that's also I know a difficulty for you when it comes time to actually turn it into a plugin, right? You have to go and undo all that stuff that we
That can be, yeah.
yeah.
So working with all this linear algebra, I know because you use it obviously because it's a very efficient way of writing stuff in MATLAB. But then it becomes
Yeah.
a case
Well,
of
it's both like computationally efficient in MATLAB, but also like efficient on your eye too, because you can like the code actually looks kind of like the math, sort of, which is good. Um,
Yeah, I suppose, Stefan, one of the reasons why MATLAB is useful for physical modeling is that you deal with these big systems that have hundreds or thousands of components, and you do have to multiply matrices and vectors all the time, and
yeah.
the matrices are sparse mostly, but then you have a lot of these calculations going on, and
Mhm.
MATLAB is just really good for it. And like you say, you can keep the notation down to a minimum because you will literally define a matrix offline and then just use that symbol throughout the code without having to roll any of the
Yeah.
calculations. And it just makes things very, very practical and like on paper. So if you unroll your
Yeah.
calculation on paper, then you can basically replicate that in MATLAB and it would work.
Yeah. Yeah, I mean, it suits me because I'm just not a programmer, Like I do it, but as a matter of necessity, Like I leave that to Craig to sort all the
do
details.
spend
Really,
quite a lot of time like unrolling
I know.
written in MATLAB. But yeah.
Well, this is one of your secret sauces, Craig, though, right? The idea that you don't rely on linear algebra libraries in the C++. You're just
No,
basically
well, the
doing all
thing,
yourself.
well, the thing is so there's always this kind of like matrix view of these algorithms, yeah. But it kind of turns out that by the time you actually move to C++, it's not the most efficient way of actually doing stuff. So using all these like sparse matrix containers and it messes up all the caching. You can't vectorize it very well. Yeah, so the first thing I do is ditch all that if possible. Like get rid of as much of the matrix stuff as I can, because then you're left with raw calculations which you can vectorize and you can improve the caching on it and all that kind of stuff. So yeah, that's normally my sort of stage one of doing any kind of prototype is, yeah, port the thing into some kind of C++ that you can actually get some kind of performance at, because we are working right on the edge of what's doable with a single core of a CPU. As much as possible, we want to get stuff running on a single core, but you don't want to be maxing it out using like 80% of a CPU core.
Yeah, that's very much of a constraint for us. But Stefan, speaking of C++, a lot of the NES code is now free and open source, right?
Oh, yeah. Yeah, thanks for the reminder about that. Yeah, so like all of our code from the NES project I mean, it's from, I guess, 2012 to about 2016, but all of the models are now available sort of open source. You can go grab them on the GitHub site. So there's lots of stuff there. There's very, very early version of what became like preparation, I guess, right? Something called Net1, which is like offline, but like really just like a real network kind of thing, a bit like Modus, like with a lot of different elements you could connect together.
Derailleur was the original thing that we kind of.
Yeah, like I guess, yeah, Derailleur also has that flavor, doesn't it? But Derailleur is from even before the NES project even. And then other stuff, like there's a guitar model that I think Gadi used a bit. Brass models. Yeah, all sorts of stuff is just sitting there.
I used all of them,
Yeah, so that's ready to use basically. So what we're doing now is we're just trying to make it slightly more usable. So one of my colleagues here, Tom Mudd, actually, that's for you, Josh. Josh knows Tom Mudd, but he's actually looking at a kind of a very kind of simple interface for trying to run these codes, right? So so that will be available shortly. So yeah, but thanks, Michele, for mentioning that.
Well, I mean, that's where everything originated from. So it's, and it's great that it's open source. I mean, I keep running into people, asking whether, whether the NES system is still up, because there used to be an online interface that you needed, access to in order to use the systems that were still hosted on a supercomputer at the time.
Yeah.
But then, that kind of stopped working at some point, and things were a bit dead for some time, but people were still wanting to use the system. And now everything has been open source, so it's great.
Yeah, our university finally pulled the plug on those computers, actually. So like we had three like big
literally,
they did actually, like big rack mount GPU things that like made 90 dB worth of fan noise, so they had their own room. And the university finally just said, okay, enough's enough. Like these are like 10-year-old GPU machines, so let's get rid of them. And then that was the moment when we decided to just go and open source the whole thing.
Yeah, I guess electricity bill is skyrocketing too, so they kind of want to keep energy consumption under control.
That's true. Yeah, that is true.
You can probably run that stuff pretty decently on a modern NVIDIA card, I presume, right? I mean, considering.
Yeah, I would think so. I don't
Is
know.
memory much of a concern?
It depends on the instrument. Like, so there's some 3D ones in there, actually, like some of Alberto Torren's percussion models. Actually, all of them are there. So he's got like the bass drum. There's multi-plate, which is it's like plates, but actually within a 3D enclosure. So you can go and put virtual mics in the acoustic space around the plates and stuff. So it's all, you can get spatialized sound out. And that stuff is going to be heavy because that.
I don't think you need a huge amount of memory because they're enclosed like little kind of like 1 meter cube.
No, none of the big room codes are there actually. So that was your stuff, Brian's stuff. Like that's separate, So but
it's
I think
mostly heavy though, those things.
That's not ever going to be real time. But I think for Alberto's stuff, but that was also hybridized, I believe, right? So there was CPU, GPU hybridization for those, I think.
Possible. Yeah, it's possible.
I forget actually how that worked. So whether that actually runs, I don't know. Like that'll depend on how your system is set up,
It would be cool to get those things running again. I have to say, like some of them. I mean, talking about parameters and parameter mapping and all that. I mean, for me as a user, as an end user, being involved for the first time back when I first met you guys, in unconstrained parameter spaces was crazy, right? Because you can do all manners of extremely interesting things, and also eventually we need to get some footage out as well of those rooms. There was 16 speakers in a room,
Yeah.
so you could render geometries with multiple positions of sampling and all that stuff, and it's really incredibly cool stuff that I don't know, I've never really seen anywhere else.
Yeah, I guess, yeah, that's another aspect of that I guess I forgot to mention is that it was really all about multi-channel sound, like doing like pieces in multiple channels. So like from 8 to 16 to 32, like stuff that could be done in like domes and stuff like that, And we did a lot of those, and it's a really cool like additional dimension to physical modeling is being able to spatialize it. Because like particularly like you have this kind of holistic kind of relationships between all the different signals coming out of some big network. Like they're all going to be related. So in some ways, like that helps to give you a cohesive images and stuff when you play them like through multiple speakers. So yeah, and so all those codes are set up to do that. So you would specify how many channels out you want, and you'd have to say like where you want to take the channels, that kind of thing, and then you're good to go. But
that informs a bit of the ethos of this thing that we're building right now, because the idea of having 4 buses and is good to have a constraint like that, but it's also the idea of having multiple correlated signals that eventually talk to nonlinear phenomena, nonlinear simulations, or generally sort of like interrelated textures, is something that again was was creatively fulfilling. It's been very difficult to stage, obviously, because the stereo version of the pieces has had its own life, but it's I did a little tour the year the record came out, trying to get as many immersive venues as possible, but those are thin on the ground, right?
Yeah.
But the concept, I mean, regardless of whether you do it in an immersive sort of multi-speaker setup, actually the concept of sort of sound design through closely correlated building blocks, with elements of simulation that are akin to ray tracing, as we recently discussed, is something that I think is still very much unexplored territory.
Yeah, totally agree, actually. So I hope that eventually we can, I mean, I don't actually know how it works. Like for plugins, can you do like, could we do a multi-channel synth? We can, right?
Yeah, we had a little go with like quad.
Oh yeah, that's right. You showed me the quad version. Yeah.
Yeah, it can be obviously a bit tricky in terms of how what listening space you're using to play it back on. But yeah, you can definitely do all that stuff.
I think it's less about having multiple outputs, because ultimately, if you're in a studio, a regular studio, you'll have 2 speakers, right, as your point of exit. So I think it's really more about, I mean, at least for me, part of the exercise with Tetrad is to try and figure out conceptual ways where these kind of workflows can be ported into a sort of more vanilla, so to speak, music production environment without losing some of the peculiarities. I mean, a lot of what has been the post-NES process has been about, sacrificing aspects of flexibility or depth for usability, right? And ultimately, I mean, this has been, anyway, for me, again, as the, in a sense, the interested bystander, to the process, seeing how these things funnel into outside of an academic context and into a, I don't want to say consumer, because that's not necessarily the point, but actually sort of like, creative use kind of scenario is really something.
Yeah, and I think that process is really valuable because we're kind of fighting systems in some sense, because there is a whole infrastructure around plugin making that you cannot really change. Because if you want to reach a wider audience, then you will have to stick with MIDI, for example, for messaging, and you will have to stick with, I don't know, VST infrastructures, stuff like that. And that cannot be changed. So those are the rules of the game. And the question is, how do you transform all that unconstrained freedom that you had from the models into something that works for a wider audience and at the same time plays by the book. So that's a process that as academic we didn't really know how to navigate in the beginning, and that's why all this experience that we collected throughout the years became really useful, because now we have a lot more knowledge about how to go about with all these things. And certainly having somebody like you, Gadi, on board is useful, because you know exactly how to navigate all this ecosystem, but you also know how to what it is like to work with these crazy systems that are unconstrained and that work basically offline. So both ends of the spectrum, and to make that connection is what you need to do in order to basically reach a wider audience, but still being meaningful to what you do. And it's not straightforward. It's not a straightforward process.
Right. Yeah. Before we run out of time, should we have a quick look at harpsichords?
Yeah, that's true. That's after all, that's
we're going to get them in.
Yeah, no, that's the title of the talk. And when we submitted the abstract, Josh, we thought this could probably be the main theme of the chat today. But actually, we kind of ventured out into different domains. But no, that's good. That's great. I mean, I love talking about these things. And there is one aspect that we haven't really talked about, which is control interfaces. So on one hand, you have the audio engine and you have the plugins, but then on the other hand, you also need to basically control them. And again, when you're dealing with MIDI, there aren't that many options. You can go MPE, sure, but then you're still kind of constrained. So, I'm going to be, a little academic now and just share some PowerPoint slides. So let's see. So I'm running another academic project now called NEMUS, which stands for Numerical Restoration of Historical Musical Instruments. And like NES, it's a Year C funded project. So the European Research Council and the European Commission that funded this 5-year-long project. And the idea was to make use of all the knowledge that came out of NES, but with a different objective in this case. So the idea was to try to restore the sound of ancient musical instruments that are sitting in museums that are completely broken and are unplayable through physical modeling. So museums do ask builders to come in and build physical copies of instruments that are no longer playable. So that's the thing, and it's been going on for some time now, and at least for maybe 20 years. Certainly because the ethics of restoration has changed quite a lot compared to what people did 100 years ago, for example, where they would take any instrument and try to restore it to playing condition just because they thought that an instrument was such only if it played a sound. But today we know that that's not the case, because obviously these are historical documents before being musical instruments. So that the documental part is mostly what you want to preserve, because you might want to know, for example, specific features of the soundboard or the braces or how the key levers are built. And obviously, if you replace them because they're broken and you want the instrument to play again, then you're losing all that information that is very, very important from a historical perspective or a musicologist perspective too. So we came up with this logo, which is very beautiful. I didn't come up with it. I just gave some ideas to a designer, and she came up with this, Paula. So she was very smart, because she designed this sort of soundboard with all these wires that are sort of in a wavy pattern. So this could be, for example, the strings of a harpsichord that are leaving the soundboard that are entering what you could call the black keys of a keyboard. But those, again, aren't necessarily just the black keys of a keyboard. For us, they could represent, for example, the sampled, timestamps that we used in numerical simulations to simulate, physical systems like musical instruments. So this idea is, this logo sort of embeds the idea of historical musical instruments and digital technology, and the wires leaving, the instrument are this, sort of very metaphorical connection between the two domains. So, there is a team, and there is me and Craig. Obviously, that is also the owner and CEO of Physical Audio, but he's also, our lead software designer in the group. And then, very talented and motivated students that are really doing a lot of beautiful work on all sorts of things. So there is no time to go into all that's been done in the group, but I kind of really want to focus on this idea of historical musical instruments. So this is a picture of an harpsichordo. I don't even know how that translates to English because the nomenclature is all over the place. But this is basically a spinet, which is a table version of a harpsichord. So harpsichords are big, but then people made smaller versions of them that are called virginals or spinets. And these are plucked stringed instruments. So you can't really see the plectra here because obviously they were removed. But through the jack slots, you basically put a jack into them, and the jack has a little tongue on it, a plectrum. So when you hit a key, the jack is released and it plucks a string. So these are plucked stringed instruments. And as you can see in this case, this harpsichordo, which is basically a spinet. Well, it's called harpsichordo in Italian, but it's not a harpsichord. It's a spinet with a polygonal shape. It's broken. It's got lots of cracks and lots of fractures. And the funny thing is that it was given to me for studying, and I didn't realize that it came from the same city as me, but it's much more ancient than me because it's almost 500 years old. So it was made by a family, the Antegnati family. These were famous organ builders, but they also made plucked string instruments. And this particular one is relevant because it appears to be one of the few instruments by the Antegnati that wasn't heavily modified through the centuries. So understanding how it was built is actually essential to understand, the building techniques of the Antegnati. So it was given to me because I made a CT scan of it. So we put it on a machine and we took X-rays of it so that we can basically see what's inside of it. And we can basically try to extract some information from the tomography scans and perhaps even sort of virtually restore the instrument without having to touch it. So there are several components within the NEMUS project, and numerical simulation is sort of what we've been talking a lot last time and today too. So that's obviously, where the audio engine comes from, okay? So you have these physical systems, for example, like the soundboard with braces of a harpsichord, or the string that is hit by like a hammer or a jack or something. So these things is what you really need to sit down and understand and be able to simulate accurately and efficiently. And that's basically all the knowledge that we're kind of expanding upon that, but that mostly came out of the NEST project when Stefan ran it. So we just inherited all of that knowledge and we sort of expanded upon it, but we had a very strong starting point for it. So real-time performance and stability are, what we really focus on in terms of numerical design. So these are really, that's really the cornerstone of what we do, and the biggest constraints we have at the same time. And that's why we can't really rely on commercial software like finite element software for it, because it's just not good for it. But then we sort of touched upon this earlier. So the numerical design that it then falls into the real-time audio, and we start from maybe a MATLAB prototype, and then we do a C++ port, and eventually that becomes a real-time plugin. We use the same mathematical models to do all sorts of things. These are necessarily historical musical instruments. That's preparation that we saw earlier. So I'm just going to go very, very quickly. I'm just going to skip. And what we did with Gadi as well is not necessarily, a historical musical instrument, but the mathematical models are the same. What changes is how you tune them, So a string is a string, and a soundboard is a soundboard. So the idea is to, within NEMUS, is to be very precise and do benchmark tests and use a lot of experimental data in order to replicate the sound of harpsichords very, very precisely, and not just a generic harpsichord, but a very specific test case, a non-playable harpsichord that is currently hosted in a museum here in Bologna by Alessandro Tagliavini, who was one of the Venetian masters of harpsichord making in the Italian Renaissance at the end of the 16th century. We sort of touched upon a lot of Gadi's stuff too, but since there isn't a lot of time left, I kind of really wanted to talk about the interface. That is surprisingly very important when you're dealing with historical music performance. So the NEMUS, one of the things we do is also to design interfaces that are appropriate for playing historical musical instruments. And at the beginning of the project, we really, this was a question that we really gripped with for a long time because we didn't really know how to make that happen. And my PhD student, Matthew, who is currently in Edinburgh, he had lots of fantastic ideas in order of how to create that. But then it became really hard because the harpsichord is very snappy, so you kind of really want to replicate that very sort of wideband effect through your fingers, and it's really hard to do with things like solenoids, for example, or other kind of electromagnetic actuators like that, just because they don't have enough bandwidth to replicate that very snappy and short contact that you have between the plectrum and the string, and therefore between the finger and the string, because as opposed to what happens in a piano, you can really feel the strings under your fingers when you're playing the harpsichord, because the plectrum is in contact with the string and your finger is in contact with the lever, with the key lever, and therefore you will feel that mechanical resistance under your fingers, and that's what you want to try to replicate. So we had a word with Andrew McPherson at Imperial College, who is also currently running an ERC project funded by the European Commission. And he's actually very much focused on the idea of creating musical interfaces for digital instruments. And he created very beautiful stuff in the past, like the magnetic resonator piano, that is basically a way to play a piano continuously. That was one of his biggest successes in terms of research. But then, we had a chat with him and we sat down with him and asked him, what would you do? And he was very blunt and he said, well, what better interface than the harpsichord itself? So that's when the idea of, getting a builder to build a new interface came into existence. And that's how we got this thing in the lab. That's a fully functional harpsichord interface. It's a function, it's got the keys and it's got the jacks and it's got everything, but it has a very small soundboard. So it's not supposed to be making a sound through, mechanical strings, and the strings are all damped. You can't see the felt here, but in normal usage, you would damp the strings because you don't want to hear any sounds coming from the strings. But then we sort of recycled one of the ideas by Andrew of using optical sensors in order to detect the jack's motion. So we came up with this very beautiful system that was actually sort of what Don Bocla did in the early 2000s with the Moog piano bar. So I didn't realize that, Bocla and Moog kind of collaborated on this little project. That's basically, an optical system to turn any piano keyboard into a MIDI keyboard. And these things were, available until a few years ago, but then somehow they stopped producing them, I think. So it's really hard to come across them. But you literally lay a strip of optical sensors on top of your keyboard, and the sensors are able to detect the amount of light that is coming in and out. And that's basically how they, you generate a MIDI message and a note on and a note off and a velocity message too. And you can, very easily, lay this thing on top of your keyboard and there you go. So we kind of try to replicate that idea by designing our own custom PCBs, printed circuit boards, and by basically embedding them inside this keyboard. And the way we track the jack motion is by attaching a sticker at on the jack's side. And there is a gradient going from all black, total black, to total white. And when the jack is moving up and down, the optical sensors receive more or less light according to how much light is reflected by the sticker. And that gives us an idea of the motion of the jack. And that's how it can generate a MIDI message according to where the jack is and where it hits the strings. So that's a very sort of, maybe not sophisticated, but smart and reliable system we found. So this is, again, I don't really want to play a sound from this because it's not very meaningful, but you can generate MIDI messages from this keyboard now. And, you can see basically the sensors when the lid is up, but normally the lid is down. So this is basically, what we do with the Nemos project currently. And it's a lot of state-of-the-art numerical modeling that has a lot of different applications, and again, this is what we inherited from we did with NES. So we're still actively working on these, very complicated models. But then the idea is to apply that to restoration and conservation of our shared musical heritage. Currently, the keyboard is hosted within the Museum of San Colombano here in Bologna. That is home to more than 50 early keyboard instruments, mostly of Italian origin. So it's one of the best places in Europe and probably in the world for early Italian keyboards. And most of the instruments are in playing condition because that was the philosophy of Fernando Tagliavini, who established the collection in the first place. He collected instruments that could be played with minimal intervention and minimal restoration. But there is this one instrument that is not in playing condition, the Alessandro Trasontino, the 1547 Alessandro Trasontino. So that's our case study. And currently the keyboard is available. So people museum attendees can go and play it. But it's currently connected to a commercial sample library. So that's all you can do is playing, a sample library. But eventually it will host our physical model once we are, done with it. And the idea is very beautiful because you're in this very beautiful room with lots of frescoes by, some of the most famous Bolognese artists. And then you have the broken instrument right at your back that you can see, but you cannot, hear. And then you have this replica just sitting next to it that is available to everybody. So you can have an idea of how this instrument sounded, and you can have an idea of what it felt like playing it because you have all this haptic connection to the instrument as well as the audio engine. So
that's why we're using this keyboard as a haptic controller.
Yeah.
Driving MIDI messages, and ultimately, we're going to use those MIDI messages to inform the physical model. That's the general idea.
I love that. Have you thought about making these into plugins?
Well, surely we'd probably release a plugin version of it, but then again, the control side of it is kind of more difficult because that keyboard is expensive. So not everybody will be able to own it, I guess. But again, you can use any MIDI keyboard to play the instruments as such. And I think that the development of this project can go both ways. So on one way, you could take, say, let's call it the basic or vanilla model of the harpsichord, and improve on it and maybe make a more creative version of it, with some kind of preparation or some kind of, nonlinear and crazy elements that we usually have in our plugins. So you could turn that into a more creative harpsichord in some sense. And that could be a commercial product, for example, that people can control through a standard MIDI keyboard. But it can also go the other way. So keeping the harpsichord sound engine as is, but changing the interface, for example. So you could augment the acoustic interface and try to implement some kind of control gesture that isn't naturally available in a harpsichord keyboard. So these are both.
You do, like both versions, have a version which is playable from standard MIDI keyboards, and then this different version which is specific to the sort of haptic interface. That's probably it. Yeah.
That sounds awesome. Couple questions. One question was from George, who had asked if you've ever tried to do physical modeling in Julia.
No, I have not. Have you, Stefan?
I have not. No. Sorry.
Sounds like no. Another question that I had was, have you ever tried using Rainbow or Maximus P? Just going straight from Maximus P into using Rainbow that allows you to compile your work in Max into a C++ project. Have you ever taken a look at that?
I've never used it myself. It looks like it has a lot of potential. I don't know how it would necessarily slot in the kind of workflow we have, because ultimately what I do is personally, Max is the upper limit of my technical abilities, so it's more about the concept and then sort of like using the prototype to convey an idea.
Yeah, nice. I'll give a couple more minutes for people to ask any questions. So if you have any questions, please feel free to ask now or forever hold your peace, as they say. So thank you very much for that awesome presentation. Yeah,
Thanks, Josh, for having us. It's always a pleasure to be here.
fantastic. So we have the next plugin that you've just announced that's going to be coming up. What other things are going to be coming up from Physical Audio?
Yeah, so we're just basically in the process of kind of reworking some of the existing stuff, because we now have like a professional UI designer, and yeah, we're going to kind of rework some of the existing stuff to bring everything up to like the professional standard we have for like Prep 2 and Modus as well. And plus, there's obviously loads of other kind of models and stuff from the Nest project still, which is all these things like things we can build on to create new plugins as well. Like things like the brass instrument stuff and all that kind of thing.
Yeah, I think it would be really good to go into wind instruments, and like the brass environment was really good. Like it had a great sonic texture to it, but we never really made a real-time version of it somehow. So it could be a good idea maybe to venture into that direction.
Yeah, and I think that's probably one of the easier ones in terms of performance too. So like much easier than doing a plate or something in terms of compute. So yeah, sounds like a good idea.
It sounds crazy. Like, I mean,
You quite
it's
like
the only,
the brass stuff, though.
huh?
You quite like the brass stuff.
I mean, it's, the conceptually it's super cool because you get to create things that are very easy to visualize, right? Like giant trumpets with plasma blowing through them. But also the sound was pretty striking, I mean, a funny piece of trivia we just received recently, a piece I made with just the brass model ended up in a nitro snowboarding video, which is, I think,
Oh yeah. Was that Black
pretty
Hole Fanfare
unusual.
or something?
Yeah, that's right. Yeah.
It was. Yeah, okay. I remember that one.
Pretty unusual for like an academic piece of computer music to end up. Yeah.
That's awesome. I mean, sounds like sky's the limit. You could create conceptually instruments that don't or couldn't physically exist as well.
That is kind of the direction that we do with physical audio. It's not specifically to recreate instruments that do exist. It's to create instruments that don't exist.
And I'm going to mention that I mean, it's good to see these ideas sort of growing, and Baby Audio released a plugin last year called Atoms that is also going into the same direction, and we know the developer, it's Sylvain, who was one of Stefan's students as well, and so he can really learn from it. And so if you use Atoms, you'll see that there are a lot of analogies with what we do, and I think it's great to see these ideas sort of growing, and more products along these lines come out. So
yeah, I love that. And there's a question from Bao. I think that we've answered that yes, but if you want to expand upon it, please feel free to. Who asked, could these model concepts be used to preserve more instruments? I'm already thinking non-Western instruments. What instruments would you say are the most challenging to model?
well, that's a good question, but
Drum
yeah.
percussion, like drums, probably just because they're kind of inherently 3D, maybe. I don't know. What do you think, Kelly?
Yeah, no, certainly. Yeah, drums are complex, but I mean, I don't know. I don't necessarily know what is. I would say probably both instruments too are kind of difficult, just because not the instrument as such, but it's the bowing mechanism that is sort of a big unknown even for academics. Like people don't really know what model you should use to model the bow.
Yeah, that's true. That's the least understood like a thing, and probably in musical acoustics, possibly, right? I don't know.
Yeah, people have done all sorts of things, like trying to incorporate the effects of rosin, and also the effects of heating the rosin whilst you're playing, So they incorporated all these thermal effects into it and tried to match experiments, but they never really quite got to one definitive model for it. So some models explain certain things, and some models explain other things, and some models work because they seem to be perceptually accurate, but they don't match the experimental evidence. So it's hard. So I would say that both instruments can be quite tricky in that respect. One of the reasons why keys, I mean, I always say that, but then I get a lot of nasty comments from, keyboard players because I always say, I chose the harpsichord because it's the easiest to model, but it doesn't mean it's an easy instrument to play as such. It just means that maybe a lot of, I don't know. It just seems
the control is simpler, right?
That's right, exactly, and that's one thing. Yeah, that's one thing. You can actually control it through a keyboard, which is a fairly standardized item, and even the MIDI framework is basically based around using keyboards for any instrument. So it kind of makes sense from our perspective to start with keyboard instruments in that sense. Even wind instruments would be complicated in terms of creating an interface for them.
I think the real problem for the NES brass stuff is just that you also have valve control too. So you've got parameters coming through your mouth, and they're all like control streams rather than events, But so you can go ahead and build a trumpet that has 20 valves, but how are you gonna play that thing, man? It's just it's hard to figure out actually. So.
Yeah, it's super hard, and I think that a lot of research in the future will probably focus more on the interface side of things rather than the audio engine, because, the audio engine is, I'm not saying it's 100% figured out, but a lot of it has been covered. So there is only this much you can do in terms of making, a better audio engine, or maybe a more intricate model, But in terms of control, that's a completely different thing, because again, we've been stuck with MIDI for a long time, and it seems really hard to get out of it. So whether we are able to design, more suitable interfaces for physical models is a question that is still, unanswered.
Yeah, and also whether it will catch on, once you develop it, you need to build a bunch of people who will actually learn how to use it and develop technique for it and stuff, and it's a long process, So probably.
Great. So it looks like we're out of questions on the chat. Where can people get in touch with you?
The Physical Audio website obviously has all the support details. I don't know, the NEMUS project also has a website.
Yeah, we have a website, so if you type in NEMUS project Bologna, will come up. So all our email addresses are there. So feel free to drop us an email if you want, or even if you want to come to the lab. If you're in Bologna, it's a nice city to visit. Come to the lab and we'll show you around.
Absolutely.
For me, I'm not on those websites, but if anybody for any reason wants to get in touch with me, is it probably through Instagram?
Great. Just look at under your name, Gadi Sassoon.
Yeah, my first and last name. Yeah. That's the one social media I'm active on. So
fantastic. Great. So thank you so much for all of that. It really looks like you're doing some very groundbreaking stuff, and we hope to see more from you soon. In the meantime, if you want to join our community, find out more about audio programming, be sure to join our community at theaudioprogrammer.com/community. I think that's it. Yeah, I think.
Join you next time, probably.
Yeah, see you next time. It seems like.
Thanks, Josh. Thank you. Thanks a lot.
Thanks, Josh.
Thank you for having us.
Yeah.
Bye.